Okay, this is the third hour of Physics 1B for our November 2nd. And we're going to look at solving this problem that we left. Okay, so I see some answers in the chat. It's like you solve for one of the pressures and you look like you solve for the work. All right, so let's see how we can go through this. So what did you all do to solve for part A? So part A says if the initial pressure is 1 times 10 to the 5 pascals and you get the initial temperature, we also know that, let's see, if we call the initial volume V1, we know that it goes to a second volume V2, where V2 is equal to V1 divided by 15. The volume is reduced by a factor of 15. Okay. So, yeah, let's go through this process. Which one of these equations did you use to solve for part 1? Part 1 wants us to find the final end pressure and temperature. So I think we need both equations, right? If we want to find pressure, we can use this one. If we want to find temperature, we can use this one, right? Because we know the ratio of the volumes. We also know initial pressure, right? So let's do it. All right, so part A. A little line right here. Part A, we know, what do we know here? Let's write down the information. So P1 is equal to 1.01 times 10 to the 5 pascals. And the initial temperature was 300 Kelvin. We have to do Kelvin for these equations. All right, a lot of people are getting the same answers in the chat, so that's really good. So for part A, we'll use equation number 1. Let's alter it a little bit here. So I'm going to write it like this. We're looking for P2, right? So I would say that if we take P1 and we multiply by V1 to the gamma, and then we divide by V2 to the gamma, that should be equal to pressure 2. And we can also write this in a slightly different way. We can just write it as P1 multiplied by the ratio of V1 divided by V2 with that entire expression right there raised to the gamma power. And we know what gamma is, as well as the ratio of V1 over V2. So plugging in pressure 1 is 1.01 times 10 to the 5 pascals. And we multiply this times V1 over V2. Let's see, V1 over V2 should be, so V2, so it's 15, right? V1 over V2 is 15. So we just multiply this times 15 to the gamma. Oh, and gamma we know is 1.4. So we end up getting pressure 2 is equal to, it looks like about 4.48 times 10 to the 6 pascals. Okay. Any questions about that part? So that's the pressure here where the the volume is decreased by quite a bit and the pressure increases by that amount, but you also have to indicate, or it's increased by a little bit more than 15 times that amount with this exponent right here. Okay, now we can use the other equation here to get temperature in a similar way. Let's just start off directly with saying that T2 is going to be equal to, looks like T1 multiplied by V1 over V2 again shows up. This time it's raised to the gamma minus 1 power. So for this, we're going to get the temperature, which is 300 Kelvin, and we multiply that by, did I do the ratios right? Let me make sure. Yeah. So V1 over V2 is 15. Raising that to the gamma minus 1 power, so that's 1.4 minus 1, which will obviously just be 0.4. And for the temperature, the new temperature now, which is increased by quite a bit, 886 Kelvin. Does everyone agree with that? I only see one person that actually put that answer in the chat. Everyone agree with that? So for part B then, let's use a different color for part B. Now we want to find the work. How much work does the gas do during the compression if the initial volume of the cylinder is 1 liter? So now, given that V1 is equal to 1 times 10 to the negative 3 meters cubed, we want to find the work done by the gas. And for that, we have that equation right there that we can use. There's another version of the equation as well, which is right here. Seems a little more complicated to me to use this one. So let's just use the temperature difference times the molar specific heat and times the number of moles. Do we have the number of moles? Well, I guess if we don't have the number of moles, we have to use this equation then, don't we? Is that what y'all found?
Mm-hmm.
Okay.
Yeah.
We could obviously find the number of moles by using PV equal to nRT, but then at the end of the day, we'd just be doing this calculation anyway. So let's use that equation. So work is equal to, I'll rewrite it down here. The work is equal to 1 over gamma minus 1 multiplied by P1 V1 minus P2 V2. Okay, so that's 1 over, gamma minus 1 is 0.4. Pressure 1 was 1 times 1.01 times 10 to the 5 pascals. Volume 1 is now 1 times 10 to the minus 3. And we subtract from this the second pressure, which was 4.48 times 10 to the 6 pascals. And then times the volume V2 is 1/15 of this, so we'll just write 1 times 10 to the minus 3 meters cubed, and we'll just divide by 15. And all of that should give us the work done. It should definitely be a negative number, because I'm sure that this quantity on the right is bigger. Yeah, like this is 1,000, not 1,000, it's like 50 times as big as the pressure, but the volume is only 1/15 the size. So you're definitely going to get a negative number here, as you did, and I believe you all got 493 joules. Does anyone disagree with that number, or do at least a few people agree with it? Yeah, a few people got that answer as well. And there we go. What does it mean that it is negative? Why is the work negative?
I would say that the force is opposing the direction of motion.
The direction of motion over the piston?
Yeah.
This is, as Kenny says, yeah, so the piston's going this way. But the force that the gas places on it is opposite to it, basically, is what you're saying, right?
Yeah.
Yeah. You could also think about it as, suppose this piston has to move in some way, right? So the piston, suppose it had some kinetic energy, and that kinetic energy basically allowed it to move in that direction. The gas is slowing it down. It's causing its kinetic energy to decrease, and when the kinetic energy of an object decreases, then the work done on it is negative. The other way to say it, as Barron says, is that the outside is doing work on the system. That's right. It's the surroundings that are compressing the gas. So the gas is doing negative work, while this force may be doing some type of a positive work. Not force, sorry. The force here is the force of the gas. The force of the piston would do positive work, but this is the work done by the gas, which is negative. Okay. There we go. So that concludes chapter 19, which is the chapter specifically discussing only the first law of thermodynamics. Okay? And as we wrap that up, we're going to move into talking about the second law of thermodynamics. And that will basically be this is the last chapter. We'll discuss thermodynamics. And from there, we'll be moving back to previous chapters to discuss waves and sound, which is a type of wave as it is. So now we're going to talk about the second law. All right. Well, specifically, we're going to talk about the kind of things we need to know about to understand the second law, and then we'll state what the second law says. Okay? But from time to time, I will say things, and I'll say, oh, this is basically the second law. So the second law of thermodynamics is interesting in the sense that there's more than one statement of it. There's a lot of different ways that you can say what the second law of thermodynamics is, and they have different values in different systems. You know, when you talk about Newton's second law, right? Newton's second law is force equal to mass times acceleration, but you also learn that force is also equal to the change in momentum of a system with respect to time, right? So the second law is like that in thermodynamics as well, that there are multiple ways that we can state it. Okay. So to set this up, what I'm going to say is that in general, it is very easy to convert mechanical energy into internal energy. It is very difficult to do the opposite. Okay. One way in which this is said. So we're starting with kind of an intro here to just the ideas that we're talking about. And the first thing I would say is that mechanical energy I suppose I should refresh what I mean by mechanical energy. Mechanical energy is basically kinetic energy of a system plus potential energy of the system. Okay. So mechanical energy can be converted into heat very easily. A really simple example of this would be you're driving along the road, you see a stop sign, you hit the brakes, you come to a stop. While you're driving along the road in your car, when you've got some time of velocity, and let's say you're coming up to a stop sign right here, so there's a sign right here that tells you to stop. Then all you need to do is to hit the brakes, and you will come to a stop, right? So you hit the brakes, and you come to a stop. So you start off with mechanical energy right here, and by hitting the brakes, there are pads that compress and whatever, but the idea is that friction slows you down, right? Friction slows you down. And the effect is that within the braking system of your car, there's going to be an increase in temperature, an increase in internal energy. It heats up, basically, right? Same thing happens if you have a box, you put it on a table, you push the box, it slides along the table until it's used up all of its kinetic energy and turned it into, heat, basically, right? You take your hands on a cold day and you rub them against each other, the motion of your hands can produce heat, right? So these are all examples of where you can convert mechanical energy of motion into heat. Really simple, right? Using friction, yeah. However, if you were to try to take the heat that develops, the temperature change that develops inside of your wheels here and inside of the braking system, you would try to take that heat and you wanted to make it so that the car could now start moving with that heat, that would be very difficult to do. Would you all agree? It's very difficult to take the heat the kind of the energy that's stored up inside of these brakes and use it to make the car again. Okay, so the opposite of this process is it does not usually happen, basically. Okay, I'll just say that the opposite, which would be heat going into motion or mechanical energy, doesn't happen naturally. So this process of mechanical energy turning into heat, so mechanical energy turning into heat, we call this a irreversible process. All right. Danny says BMW has a tech that converts the friction from braking when you're going downhill into energy. What kind of energy? Do they use it to heat up the car? Or do they use it to... So while you're typing that, Tom says, what about water boiling? So in water boiling, you're taking heat flow, you are putting it into the water, which means that the water will now increase in temperature. And so you've basically taken heat and you've turned it into, temperature increase. But have you turned it into mechanical energy, Tom? Individually, the molecules themselves may have mechanical energy. But that mechanical energy is manifested as a temperature increase, not so much as in motion. However, we can use boiling water to do this, which is what we're going to talk about. That's the main way in which we're going to use boiling water, and when it phase changes into steam, the motion that it produces to make mechanical energy. But yeah, we call these type of processes irreversible processes. Okay, so Cam says the flywheel under the car. Yeah, I'll have to. We can talk more about this technology you guys are talking about. I'd never heard of it before. You found it out yesterday while driving with a friend who borrowed a parent's BMW. Okay, yeah. So let's look more into that. We can talk about it next time for sure. I'm very interested in knowing what they're doing with that, because if there's a way to, so the idea that you're talking about is you're going downhill, but you're not just freely going downhill. You're braking as you're going downhill to maintain your speed, and then you're taking that energy of braking, that temperature increase, and you're using it to somehow increase the efficiency of the automobile. Maybe that's a very interesting idea. Okay, so these processes in which mechanical energy turns into heat, we call them irreversible processes. And I would say, in general, that processes that occur naturally are usually irreversible. Delvino is saying, you know that it charges your hybrid car's battery when you hit the brakes. That's really interesting. That is really interesting. But it also charges your battery when you're moving. So, yeah. Right? I mean, everybody's battery charges while you're moving, right? That's even non-hybrid cars. That's how it works. Like, if you ever had your battery die and you need to get a jump, right? You get the jump, and then if you leave the car running and you drive around for a while, you can recharge your own battery, right? Get on the highway, drive for a little bit, you can charge the battery, and that process uses a generator to make that happen. If you want to learn more about generators, we'll learn a little bit about it in this class, but they work off of electromagnets. Okay, so processes that occur naturally are usually irreversible. Okay, an example of a natural process that's really simple would be the flow of heat from a hot body to a cold body. That's an example of an irreversible process. And to compare that to reversible processes, a reversible process would be one in which you could convert mechanical energy into heat and then take that heat and convert it back into mechanical energy. A reversible process is kind of an idealization that doesn't really exist. So does this part make sense? Flow of heat from a hot body to a cold body. We call that an irreversible process because heat never really flows from a cold body to a hot body unless you put work in, right? Your refrigerator operates off this principle. That's what a refrigerator does, is it makes things colder, yeah? And the only way to make something cold, let's say you take a hot can of soda, you put it in your fridge, you wait a few hours, it's cold now. How did that happen? Well, the refrigerator was a colder temperature. Why is it a colder temperature than its surroundings? Because it's constantly pumping heat out of the refrigerator. That's the sound when you hear the refrigerator running. So you need an external... So when I say irreversible, I don't want you to think that it's impossible to reverse, just that irreversible means that this is the natural direction in which processes flow, okay? And I think I can say... I'm pretty sure this is true. Yeah, any process that occurs naturally is guaranteed to be irreversible. Okay, let's think about what reversible means. Let's just take a second to think about what reversible means. So let's think about some really simple systems. So let's take. Tom says it's like water flowing uphill. It can't happen without humans doing something. Yeah, pretty much. Or if it has enough energy because it was flowing downhill long enough and then it could flow back up, but it can only go so high, right? So let's think about some things that might perhaps be reversible. So let's look at something simple. Let's look at a pendulum. What is a pendulum? You've got a fixed point from which you suspend something like a string, and then you put a mass on the end of the string, right? And then you take this string and you pull it to some position like right here, and then you let it go. And it swings back and forth and back and forth, right? Now, if this was a reversible process, what would happen would be that if you swing it to some height here, above which it starts, some height that you call h, then that it would swing back over here to exactly the same height when it gets to this position here. And then it would go back and forth and back and forth, and it would never go to a lower height, okay? That would be kind of a perfect pendulum, right? The reality is, when you take a ball with a string on the end of it and you pull it to the side, it will oscillate back and forth, but each time it oscillates, it loses some energy, right? It loses energy because it's attached to a pendulum, it's attached to a point at the top. That point is going to have some kind of a pivot that allows it to swing back and forth. If that pivot is your hand or anything else, there is guaranteed to be some kind of loss of energy that goes into the pivot itself. If the pivot is composed of, something that swivels back and forth, there's going to be internal friction. That internal friction is going to tend to dissipate the energy of this pendulum. If the pendulum is swinging through the air is going to produce resistive forces as well. The air isn't going to speed the pendulum up. It's going to slow the pendulum down over time. Maybe not very much, but it will due to drag forces. And over time, this pendulum will eventually come to a point where it's not oscillating back and forth anymore. And this is because there is some heat exchange with the environment that occurs at the pivot, some heat exchange that occurs with the environment through the motion of the pendulum through the air itself, through the air molecules, and so this pendulum will not swing forever, right? So if it was reversible, since I'm saying reversible processes are an idealization that's impossible to reproduce, a reversible pendulum would be one that swings forever, right? In, I don't know, things that you've read or seen, this type of thing would be called a perpetual motion machine, right? Have you all heard that expression before, perpetual motion machine? So perpetual motion machine would be something that would be a truly reversible system, one which it would never lose energy, all that kind of stuff. But what we're saying right here is that reversible processes are impossible to reproduce. You are always going to have, this is what the second law of thermodynamics says, you're always going to lose some amount of energy, especially in the cases in which you try to take heat energy and convert it back into mechanical energy. All right? Which is what ultimately this chapter is about. This chapter is about, it's about trying to do this. It's about, in a way, trying to cheat nature, you know? We all try to get other people to do things for us in our lives, right? When we're growing up, it's our parents that do things for us, or our guardians, or some type of person who is responsible for us, and they do things for us. And then as we get older, we start to rely on machines to do things for us, like computers to do calculations for us, or Wolfram Alpha to solve our integrals for us and stuff like that. And later on, maybe we learn how to drive a car, and now we have a car that does work for us, right? It allows us to drive around. We're a very lazy species as humans, and we want to find ways to cheat nature into helping us do things for free, effectively, or maybe not for free, but for some kind of cost that we're willing to pay. And within that cost, at its core, is the ability to take heat, which is something we can produce very easily, and turn it into mechanical energy, right? Your car does this. You go to the gas station, you buy fuel, you put the fuel in your car, and now you can drive some number of miles. Say, like my car, I think I can go about 300 miles on a tank of gas, right? So that is a conversion of the energy of the fuel, which is burned in the engine, and it then turns that energy that we burned into mechanical energy. The car moves, right? And that's what the second law of thermodynamics is about. It's about the fact that when you do this, when you try to convert heat to mechanical energy, because it's the result of an irreversible process, there will always be some amount of energy that you lose in this process of going from heat to mechanical energy. There's no way to get around it at all. It is part of the way the universe works. You're never going to get as much energy out as you put in a type of thermodynamic process, right? Never going to get as much energy out as you put in. The pendulum is almost, you can almost get out what you put in if you think about it, right? Because when you lift the pendulum to some height and the pendulum swings back through the middle here, it converts potential energy into kinetic energy, and then back into potential, and then back into the kinetic, and then back into potential, kinetic, potential, kinetic. But the whole time, it loses just a little bit of that energy. And that small amount of energy that's lost in this process is what makes it irreversible. Because at the end of the day, the pivot is going to heat up, right? And if this was a reversible process, we could take that heat, and then as maybe this BMW they're describing does, we could use that heat to lift the pendulum back up, right? But that doesn't happen. It's never going to happen, right? To take the heat at this pendulum right here and to use it to cause this pendulum to get more energy, it's just not going to happen, right? Okay. So there's a picture here that kind of shows what these processes look like. If you're going to have a reversible process, it requires that the system roughly stay at equilibrium, okay? In order to, I'll write that down right here as we talk about this. So a reversible process, where did I write down? Oh, must be very close to equilibrium, thermal equilibrium. with the environment with only small temperature changes. Can you see how the pendulum is an example of that? Like, you're going to have very, very small temperature increases. Probably hard to measure temperature increases at the pivot right here, right? Only small temperature changes, right? But we got to put it in a kind of thermodynamic perspective, right? So that's what this problem here does. Okay, so A is irreversible, B is reversible. So irreversible for part A. A block of ice melts irreversibly when we place it in a hot 70 degrees Celsius metal box. So you've got ice at 0 degrees Celsius. You've got a metal box that contains the heat inside of it at 70 degrees Celsius. The water is going to melt. Heat flows from the box into the ice and water. Never the reverse. This is what makes it irreversible. So the ice, which was at 0, is now 40 degrees Celsius. The metal box is 40 degrees Celsius. You reach thermal equilibrium then, right? It's never going to be the case that the liquid water that's in here would just randomly go the other way, you know? That just all of a sudden the molecules decide to start organizing and they form an ice block. But okay, ice doesn't exist except for 0 degrees Celsius, so now this water is going to have to expel some heat, and then the process, you know, the box heats up, right? A reversible process must be very close to thermal equilibrium. The reversible process must be very close to thermal equilibrium with the environment with only small temperature changes. Does that help, Baron? Okay. Now, okay, so everyone's on board with this idea that liquid water at 40 degrees Celsius inside of a metal box that's the same temperature, this is never going to proceed backwards to where you're suddenly going to get ice, right? Everybody agrees with that, right? Okay. Now, take the same system, but make it in thermal equilibrium. That is to say, keep both the objects at the same temperature, right? So you've got the metal box at 0 degrees Celsius. You have ice at 0 degrees Celsius, right? A block of ice at 0 degrees Celsius can be melted reversibly if we put it into a 0 degrees Celsius metal box. So we have ice, we put it into a metal box, and it says by infinitesimally raising or lowering the temperature of the box, we can make heat flow into the ice and melt it, or make heat flow out of the water and freeze it. So by taking metal box at 0 degrees Celsius, if we increase the temperature of the metal box to 0.1 degrees Celsius, it should melt the ice, given enough time, right? It should melt the ice. But this feels like such an oversimplification, but we're gonna stick with it. It does, Ruja. The question is, does entropy have anything to do with irreversible processes? It has everything to do with it. Yeah, absolutely. We're gonna get right to that next. That's the next thing we're gonna talk about is randomness. So there's a lot of problems with this that I immediately see. First of all, if you have a metal box at 0 degrees Celsius and you have ice at 0 degrees Celsius, yes, it could technically cool the ice could technically turn to water. I guess the idea is that you just raise the temperature of the metal box by a little bit, some of the ice melts. You raise the temperature of the metal box by a little bit, the ice melts. So the whole process occurs at the same temperature. You don't have really any temperature changes occurring. And yeah. And then once you've cooled the liquid water, and you've got liquid water, you could imagine now if we decrease the temperature of the metal box by just a little bit, then it should be able to freeze some of the water, and you decrease it by a little bit more, freeze a little more water, etc. So this would be, I mean, this is an example of a reversible process. It's an example of where the idea is that if you keep it in thermal equilibrium, there's a potential that you could reverse it. But it would not occur naturally, right? You'd have to raise or lower the temperature externally to make it work. Anyway, reversible processes, they're not real. And part of the reason why is due to what you just said, Ruja. So we'll go directly into that. So the direction of a process, the direction that it flows, is going to be related to randomness. if we think about like free expansion of an ideal gas, free expansion was this picture of you have a gas in a container and you just let it expand to fill its environment. Free expansion leads to more disorder. You've got more molecules occupying a larger volume. Those molecules are then going to be more disordered. They're spread out. They occupy more volume. Yeah. And the conversion of mechanical energy into heat that we just talked about also leads to more disorder. This also is a process that produces more disorder. The science word for disorder is entropy. Entropy is a measurement of disorder. But in general, we can just say that that the direction of a process is related to randomness. Almost all processes occur in such a way that they lead to more disorder. Take ice, right? Ice is like a crystal. It's very ordered. The molecules are in very specific places and stuff like that. The disorder increases. You could, in a very simplistic way, you could say that you have order when you have the ice molecules. Nice little crystalline, lattices. All the molecules are all kind of lined up on very specific points. The volume of the ice itself is fixed, right? It doesn't really compress or grow in any way. And the shape is also fixed, right? With liquid water, the molecules are now zipping around all over the place, right? They're moving all over the place here, and that means they are more disordered, basically, right? This increase of disorder is measured through entropy. In a very simplistic way, we're gonna learn more about entropy in this chapter. This chapter, in many ways, is about entropy, and entropy is effectively a measurement of. It's a measurement of disorder, but what does that mean? How do you measure disorder? It turns out you measure disorder by measuring all the possible states that a system could occupy, and then that's how you measure disorder. It's related to the number of different states that a system can occupy. But we'll get more into that later. For now, there's a connection now between these processes. We say they're irreversible, and it turns out that irreversible means that you've basically gone from a system that was ordered, and now you have a system that's disordered. Okay? I think one of the simplest examples of this is, imagine you take a glass and you hold it above a concrete floor and you drop the glass. It shatters into thousands of pieces on the floor. When all that glass was formed as a glass, it was ordered, right? Now that you have all these pieces of glass that are separated out on the floor, they're disordered, right? And here's how you can connect it to reversible. While a glass can fall off a table and shatter into thousands of pieces, you would never see those thousands of pieces naturally realign themselves into a glass, right? Someone would actively have to put energy in to reorganize those pieces, right? I think you could apply this to a puzzle as well, right? Suppose that I have a puzzle that's been done, like a jigsaw puzzle that's been done, and someone comes along and they break it all up. Those puzzle pieces will never randomly just form into a puzzle. You need to actively think about and organize them, right? So that's how randomness is related to irreversible, and how it's related to the direction that a process undergoes, right? Processes will go in one direction, and the direction they will go in is in such a way to increase the overall randomness of the system, the overall disorder of the system, and yeah. Does this part make sense? Why is the conversion of mechanical energy into heat, why does that produce more disorder? And let's just look at like the simplest possible example. I've got a box, it's on a surface, the surface has friction, okay, and the box starts off moving in this direction here with some velocity, and there's friction down here on the bottom. So as a result, this box eventually comes to rest, right? So it moves to a point where it has a velocity that's equal to 0. And how is it the case that as the box slows down due to friction, how does that produce more disorder?
Like the little molecules begin to kind of shake more.
Yeah, so you've got molecules down here in your table, and as this thing slides by, they start to jiggle. Right? They're all vibrating. They're all just jiggling and jiggling and jiggling. And the fact that the box slowed down means they've got to be jiggling a little faster. It had kinetic energy, now they have kinetic energy. And taking the kinetic energy of a single box and converting it into the kinetic energy of trillions and trillions of molecules that are all randomly moving in different directions, well, that's a lot of disorder down here compared to just a box moving, right? You have a single object with one velocity, and all of a sudden you've got trillions and trillions of objects with all kinds of different velocities. So that's where the disorder is coming in, is in the heating up of things. And if you think about it, temperature increases, right? We've learned are related to an increase in internal energy, and that internal energy takes on the form sometimes of kinetic energy, sometimes also of some type of potential energy within the molecules, or between the molecules. But that temperature increase, right? It naturally increases the random motions of the molecules. So a temperature increase is automatically associated with disorder. So if you have a system that converts any type of energy into heat, then it's guaranteed that you're increasing disorder, because now you've taken a macroscopic system and started to move around a bunch of microscopic molecules. Okay, so does anyone have any questions about what an irreversible process is and what a reversible process would be? Reversible process has to occur very close to thermal equilibrium. We're going to need to use this idea when we're discussing heat engines. An irreversible process is what most processes are. Most processes that occur in nature are irreversible. They happen to correspond to an increase in disorder, and they are what we call natural processes. And again, to reiterate that, a glass can fall and break. It is very difficult for the individual pieces of the glass to reform themselves. Ice can melt. It is virtually impossible in and of itself for a hot object to suddenly absorb energy from a same temperature object and then suddenly become ice again. That doesn't happen. This process will never go the other direction unless we actively make it happen. All right, any questions? We don't have a lot of time left, but we can kind of introduce some ideas here that we'll develop more next week. So the next topic is heat engines. Okay, so a heat engine answers the following question. How do we convert heat into mechanical energy? How do we take heat and turn it into motion? All right. Examples of heat engines would be like your car, would be like a power plant. Maybe you can think of other examples. What's an example of a heat engine that you can think of? It's an object that's going to convert heat into mechanical energy. And I would say one example would be the internal combustion engine in a car. A power plant that burns, well, anything. A train, a Stirling engine. What's a Stirling engine, Cam?
I believe that's like when you put it on the palm of your hand, if I'm thinking right.
and it starts to move based on just the heat of your hand.
Yeah.
Okay. That doesn't. I mean, that phrase seems similar to me, but I don't remember off the top of my head what it is. I'd have to go look it up. All right. So the internal combustion engine in a car, a power plant, converts heat into mechanical energy. And a power plant then takes that mechanical energy and it turns it into electricity, which you then use to power all your devices. So at the core of anything, like the computer that or the phone that you're watching this on is being powered by a heat engine. All of our world is basically powered by giant heat engines that we call power plants. Okay. So what are the kind of pieces of a heat engine? So a heat engine will always have some quantity of matter that it's going to extract heat from. Okay. It has some quantity of matter and this quantity of matter is referred to as the working substance. As it's ultimately going to be the thing that does the work for us. And it undergoes a process that basically looks like this. It starts off as heat comes into the substance. Followed by the heat being expelled to some external system. So the heat comes in, and then that same heat, some of it is expelled. I'll say some heat is expelled to an external something. I'm going to call it a reservoir. Something that can take on this extra heat. And then the idea is that the heats are different. So there's heat that comes in, there's heat that goes out, but whatever the difference is kind of where we're going to get the energy. But the idea is that this heat difference then basically is used to produce compression of a gas, expansion, and sometimes phase changes. That do work. That is basically what a heat engine is. You take heat into your substance. Some of the heat is expelled to a external reservoir, and then the difference between these two is used to produce compression, expansion, and phase changes that do work, basically. Okay? And we'll also say that there are cyclic processes. This would be one in which the working substance is returned to the same state after the process. So you can repeat it over again. And so if in doing this process of 1 to 2 to 3, you end up coming back to 1, then we call that a cyclic process. I'm just going to go ahead. We have such little time here. I don't want to go into the details of this stuff. I'd rather just go into showing you like what a heat engine is. Okay? And I'm going to look at specifically like a power plant. All right? So how does a power plant work? So we take coal or gasoline or something. So we take a fossil fuel. It doesn't have to be a fossil fuel. It could be heat produced by a nuclear reactor or whatever. We start off with some fossil fuel. This is not the working substance. This is going to be the thing that we burn to provide heat. So the fossil fuel, we light it on fire. And we connect it up to our working substance, which is going to be water. So we have some vessel. And within our vessel, we're going to have water. The water is the quantity of matter, the working substance that we have. Okay. The water is heated up, obviously, by the fossil fuel. It then produces steam. That steam flows out. Whoops. That steam then is going to flow out of a spigot. The idea would be that you have the spigot kind of go down just like a kettle on a stove, and the steam is going to flow out this way. So steam comes out like this. Let's use the same color so it's clear that it's the same substance. So the steam basically flows into this pipe. How do I have two things selected? Okay. The steam flows into this pipe, and it kind of sprays out here. Right? And then the steam is going to be coming out at like really high speeds. So what you do next is you connect this up to a turbine. So we've got a turbine right here. And the turbine is now going to start to move. So the turbine is going to move, motion, i.e. mechanical energy. All right. Now, if we do this long enough, the water will eventually run out, right? So what we can do is we can make sure that our steam that's coming out of here, we can basically take our steam and we can recollect it in some way, right? How could I draw this? So now we need to catch our steam, right? So how are we going to catch the steam? How can we reuse this steam that we get out of this?
We basically have to like cool it down.
We need to cool it down, right? Okay. So I said there's, again, let's look at this process. We have a working substance, that's the water, right? Heat coming in. Where's the heat come from? It comes from the fossil fuel. So this is our Qn. Like this. So heat comes in, we get energy, it's moving, but we need this process to kind of occur in a cycle so we can keep it going, right? So the heat needs to be expelled to some external reservoir. This is going to be our cold object. We need a cold object to cool this down. So, I don't know, maybe we've got some type of device that catches our steam and cools it down. So you've got maybe, I don't know, maybe we've got a cold piece of metal right here, cold plate, that the steam basically hits this cold plate, right? And then maybe we recollect the steam as it drips off here. So droplets form on this thing. Those droplets then maybe get collected in some type of device down here. So we get more water, but then all we need to do now is we just need to have a pump to get our water to kind of flow back into here, right? So droplets of water, they condense, we collect that water in some type of a pool down here, and then we pump the water back in here, and then we reuse it again, right? So you've got Q in here. Where's the heat going out of the system happen? Where does the heat go out of the system? So I said the process was heat comes in, heat gets expelled to external reservoir, and the heat difference is used to do work. The cold plate, yeah, okay. So what I'm going to say is I'm going to say that the fossil fuel starts off. That's not really the hot part. The hot part is the hot water. Draw. Here, let me erase this real quick. It's the hot water that's hot. This is water this is the hot temperature. And it's going to flow into this, and this is going to be the cold temperature. So this is the T cold down here, I think, for the way that we're going to talk about this in the future. But yeah, this is our cold reservoir. And then this is our hot reservoir. So hot reservoir, hot water, cold water. And it's within this temperature difference that you get work out of the system. It's within that temperature difference that we're going to get work done. Okay? And the cold reservoir is going to be where the heat's going out. So we'll just put that right here. And there's going to be some amount of difference between the heat that goes in minus the heat that goes out. But with the way we've defined these things, technically it would be plus. But the way we're going to write this is to say, if I take the absolute value of the heat that's coming in minus the absolute value of the heat that's going out, this is going to be equal to the work that's done in this process. And that is basically a heat engine, or at least my attempt to draw one. All right. The book, of course, has some nice diagrams, and I can pull that diagram over here. If I can find it. So the book's diagram looks like this. This is a schematic. You have a hot reservoir at temperature TH. Heat comes in. Some of that heat goes to the cold reservoir here. And whatever work you get out of that has to be related to the temperature difference. Not the temperature difference, sorry, the difference in the heat that came in versus the heat that went out.
So is the priority to get the coldest reservoir out of the system to get the most work done?
Yeah. Well, I would say... So we will relate this to temperature differences here in a second. What did I write down about that? Let me see. I think that the answer, like the simplest answer, is yes. That the colder that this is, the better. I don't think it's that simple, actually. Maybe we could think about a system in which that might be true.
Mm-hmm.
But if you think about it, all that the cold reservoir really does in this case is to condense the water so it can be used again, right?
Mm-hmm. And you want that to be able to be like kept cold.
Sure.
Mm-hmm.
So I guess in that sense, the fact that the cold reservoir needs to be able to stay cold, yeah, in that sense.
Mm-hmm.
But what I would say is, if you look at the way that this equation works out, you have input of energy in terms of burning the fossil fuels, right? It increases the internal energy of the water to the point where there's a phase change. Once that phase change occurs, the water has a lot of kinetic energy that you can extract. You extract the kinetic energy via a turbine. What I notice about this equation is if you want to get the maximum amount of work out of this equation,
you also get heat in, yeah.
What's up?
Or you could just have like a massive amount of heat in.
Yeah, that's part of it, is that you have heat that's coming in, right? You could increase this. It's the difference between the two that matters, though, right? So reducing the amount of heat that you could think about this as this is the heat that you lose in the process, basically. Right? The heat that goes into the cold reservoir is basically the heat that you're losing in the process. So if you could get that to zero, that would be the best way to get all the work out of the system, because then you wouldn't really be losing any energy, right?
Mm-hmm.
But the reality is you can never do that. You're always going to have to expel some amount of heat in these processes. That's another version of the second law of thermodynamics, which is that a heat engine operating in a full cycle is never going to be 100% efficient. You're always going to have to expel some of the energy that you put in. Which means, since you're always expelling some of the energy that you put in, you always have to keep supplying energy. Which means that eventually, the system won't work anymore, right? Because eventually you'll run out of fossil fuel, and you'll have to find some other way to heat the water up in order to make the process occur. This is why fossil fuels are really valuable, because we can use them to do this, and they're easy to extract, and the amount of energy that we get from burning them is really large compared to the amount of mass that we need to transport around. So Tom says this is where nuclear comes in. Yeah, this is where any other form of energy production comes in, but this is the primary way in which we produce energy. It's also the primary way in which you drive around, right? Now, the internal combustion engine of your car is different, and we'll talk about it next time, but, we're at time. It's 1:10. So let me stop the video now, and then I can keep talking after that.